All right, so like I mentioned in the previous video, we're thinking of power series as these infinitely long polynomials, but they're functions nonetheless. So the first thing we're going to do is really start treating them as functions. What did we do to functions before in calculus? Well, we did things like differentiate and integrate them. So let's just go through how we can actually differentiate and integrate some of these so-called power series. So let's go through this. And the example I want us to do is the example we sort of looked at up above, was this function g of x that we're writing as a power series from n equals 0 to infinity of the series 5 over n factorial, all times x to the power of n. And in fact, we even wrote above some of its terms before, so I'll just copy down some of its terms. So we had things like 5 plus 5x, plus 5 halves x squared, plus 5 6 times x cubed, and so on and so forth. And the reason I want to point this out is, if we look at what's really going to happen here on this right-hand side, these really are like infinitely long polynomials. And well, if we're going to do some calculus with these infinitely long polynomials, we know how to differentiate polynomials, we know how to integrate polynomials. So we're going to get to use a lot of these power rules or anti-differentiation power rules to help us out here. So let's actually go ahead and just dive right in. Let's first differentiate this function. So we're going to take the derivative. And well, when we take a derivative of the function, we can call this g prime. We can think about doing this a couple ways. I'm going to introduce what I call a derivative operator, but we're really going to see what actually touches this differentiation operator. So a d dx, where this is basically saying, you know what, I'm going to take a derivative on whatever's on the right-hand side of me, but with respect to x. So again, we're taking the derivative of both sides of that g of x equation. G of x equals that power series thing. We're taking the derivative of both sides. That left side is just g prime. That right side, we're going to hit with the derivative with respect to x, which is what that d over dx represents out in front. All right. And the next thing I want us to notice is, if we bring this derivative, this d dx inside of that infinite series, it's only going to act upon things that have x's in them. So for example, it's going to move right beyond that series notation sum, sigma. It's going to move beyond that n over, or 5 over n factorial, because the only thing with an x inside of that series is that x to the n. And just like we would do with any power rule, since we have x to some power and we're differentiating with respect to x, we bring that power down in front and we raise x to a power minus 1. So in this case, the derivative of this example power series is n equals 0 to infinity of 5 over n factorial. So that part didn't change. But then when we actually take the derivative, we're only differentiating that x to the n, which will give us an n times x to the n minus first power. So just like we would do with any power rule, if we had x to the third and we differentiated it, we would get 3 times x squared. In this case, we have an x to the n, so when we differentiate it, we get n times x to the n minus first. And that is actually the derivative of this particular power series. And if we took the derivative of the thing up above, well, we would actually see that these things work out the same way. So if we differentiated just that right-hand side where we actually started writing out terms, we would see that it matches up exactly with what we just did. In fact, we would see that this derivative would be 5 plus 5x plus 5 times 3 all over 6 x squared, and so on and so forth. So differentiating power series aren't actually that scary. It's just going to be a bunch of derivative power rules that we do. And just like we saw before, we're really only going to differentiate the stuff with the x's in them inside of those power series. All right, so let's do another example. Or actually, let's keep the same example, but this time, let's find the antiderivative. So in this case, we're looking at the antiderivative of our function g of x. So again, let's write out both sides. We had our original g of x power series was a series from n equals 0 to infinity of 5 over n factorial, all times x to the n. And well, I'm going to come across here and I'm going to take the integral of both sides with respect to x. So this is similar to what we did before when we took the derivative of both sides. Here we're just now taking the integral of both sides, basically looking for the antiderivative. So let's ask ourselves, we are taking the antiderivative with respect to x. The only thing inside of this entire series with x's on it is, well, that x to the n term. So we can really pass this integral operator or this integral sign into the sum. It passes the summation sign sigma. It'll pass the 5 over n factorial. And in fact, it'll just touch and affect that x to the n term. And what this x to the n term is, well, this is x to some number. So if we do the antiderivative, we get to use the antiderivative power rule, which in this case, we can write that series summation 5 over n factorial, the series n equals 0 to infinity. When we take the antiderivative of x to the n, we're going to get x to that power plus 1 divided by that power plus 1 as well. So we get x to the power plus 1, in this case an n plus 1, all over n plus 1. And well, since this was a indefinite integral, we also get to tack on an integration constant. So when we integrate power series, we're actually just going to be doing a lot of antiderivative power rules. No matter how complicated that series coefficient is, like in this case 5 over n factorial, or it could be something very ugly, if there's no x's in it, the integral won't touch that part. It's really only caring about whatever that x to the power is. So that's how we can start doing calculus with power series. So it's nice when we have power series representations of functions, is we can actually do calculus on them in a rather straightforward way, because it's just going to be a bunch of differentiation power rules or a bunch of anti-differentiation power rules.